With gravity, we didn't have potential. We only had potential energy. You lift something up in a gravitational field, and we said it has some potential energy, right? There's a force acts on it. And we say it has some potential energy due to its location in that gravitational field. G, little g, is the gravitational field. How do we find the force? We multiply the mass times the field, G. So with a charge in an electric field, there's our electric field. I'll make it a positive charge. So there's a force in an electric field. That positive charge is going to feel a force on it if it's in an electric field. Positive charge feels a force in the direction of the electric field, right? And that force is equal to its charge multiplied by the electric field, just like F equals mg, the mass multiplied by the gravitational field. And if we move this charge by some distance, d, so it's over here now, it's like lifting a mass up in a gravitational field. It now has a longer distance it can move. If there was some obstacle here, the positive charge could move this far before hitting the obstacle. Now it can move a bigger distance, right? So it's going to have more stored energy now. So if we let go of it at the higher location, it'll have more kinetic energy when it hits the obstacle. Kind of like a mass. If we bring it up higher, the gravitational field can work on it over a longer time before it hits the floor. It has more potential energy at the higher location. So how much energy? So this is our U sub G, was mgh. And now we have a U sub E, our electrical potential energy, and it's equal to the work done in moving the charge. Just like this one. If we move it up higher, then it's the force times the distance, right? The work done in moving the charge is how much energy is now stored in that charge. So over here, the force times the distance gives us the amount of added potential energy. So the potential energy, I guess I should put a delta there. The change in potential energy, because it actually has potential energy here too, because it could, if we let go of it, it's going to start moving. So the change in potential energy as we move it up is going to equal QED. So at this point, we stop with gravitation, right? That's it. We don't need anything else. But we go a step further with our electrical charges. We want to get rid of the dependence of the charge. We want to try to think of what is happening because of the electric fields, not because of the charge we're moving. And so we want to divide that out. So we divide our potential energy by the charge. And what does that give us? That gives us some new quantity we call potential. So we've divided out the effect of the charge that we're moving. This is handy if we're going to move a bunch of different charges, like in a circuit, when the current changes. Sometimes the current is small, sometimes the current's big. We don't want to have to redo the calculation as the current is constantly changing. We want to do the calculation once, and then if we want to know the energy, then we multiply it by the current at that time, right? We can multiply it by Q later. So the potential, change in potential, is just the change in potential energy divided by Q. We've divided out the effect of the charge that we're moving, and it only depends on what's creating the electric field. Okay, and this is equal to work done over the charge, because work equals negative delta U. So we get that. All right, the units for potential. Not to be confused with potential energy, are volts. And what is that? It's a joule over a coulomb. You can see that from this expression right here. Energy is joules, charge is coulombs. A joule per coulomb is a volt. Okay, and there's one more relationship that's handy. And that's how, when we move a charge through an electric field, the work done, I just did it, right? The work done is Q times E times the distance that we've moved it, right? The change in position, right? The distance that we've moved it. And so what do we end up with for our voltage? Our delta V is going to be, because it's negative W over the charge, right? I just had that written up here earlier. I'm going to plug in what W is, and we get negative E delta S. So we have this relationship. The electric field is the rate of change of the potential with distance, whichever one of these you like. So the key, there's a couple of key. One of these two expressions, those are the same, however you like to think of it. And then this expression, those are two key ones that you're going to use a lot in going back and forth between potential energy, potential, work done, and electric field. Okay? And we've used these already. The example we did the other day where we had, what was it, a rectangle. Two corners of the rectangle had charges that were fixed in place. One corner had a charge that we moved, right, from one corner to the other. And we said, what was the work done? So we found, in essence, we were doing, right, this relationship right here. We found the difference in potential between those two corners, multiplied it by the charge that we moved, and then we had the work done in moving the charge from one corner to the other. Okay, does that help a little bit? We good with that? Just as a quick example, let me show you, because we ended with capacitors last time. Let's look at a capacitor. Capacitor has two conductive plates. And on one plate, we're going to have some positive charge stored. And on the other plate, some negative charge. And what's in between there? An electric field, right? Fills that space. If the capacitor is big enough, if those plates are big enough, really big compared to the spacing, I know I didn't draw it that way, but if those plates are really big compared to the spacing, it's as if they're infinite sheets, right? And if they're infinite sheets, if they're really big compared to the spacing between them, our electric field is nice and constant in here. That's our electric field. So the electric field's constant. If we were plotting it, versus our distance, I'll just call it x, then the electric field's constant in there. And what is it outside? 0.